The other type of wave, or specifically standing wave, that we're going to talk about is standing sound waves, and specifically in pipes. We're going to talk about two specific situations: an open pipe, and we're talking just a straight tube of some sort. If you've ever had the paper towel tube, for example, or a wrapping paper tube, or even a toilet paper tube, when it's empty, just tap it on something. When you tap it, you hear a certain pitch. And that specific pitch is directly related to the length of that tube or pipe. So by open pipe, we mean both ends are open. So the sound is going to travel through the pipe. So these sound waves are going to travel on through, but wherever there is a boundary, so even just right here, where it goes from having no tube to having the tube or pipe, and then this other end is considered a boundary as well. At these boundaries, these are considered loose boundaries. As a reminder, let's jump over here. Now, this is a string, but it still represents the loose boundary. I don't know if you happen to remember, the fixed end is what we were showing and talking about when we were talking about the standing wave on the string. So the wave, it travels when it reaches that fixed end, the wave inverts. If we have the pulse, but we have a loose end, the loose end is free to move. And so with this pulse, it does not invert. So this is a string, yes, but the concept is similar in that when a wave, the sound wave, reaches these boundaries, there will always be some reflection, and the open boundaries are loose boundaries. Meaning when the wave reflects, or any portion of the wave reflects, it will not be inverted. What that means for the standing wave in the pipe is that these ends are antinodes. So the ends, open ends, are antinodes. So if you think antinode, with the wave on the string, the antinode is where we had the constructive interference. So if we could see the air molecules near the end, they would be spread out quite a ways away because they would have the most movement. In the middle, we would end up with a node where we don't have as much movement. It's hard for me to visualize longitudinal waves with the compressions and rarefactions. So I personally like to go ahead and draw just the sine wave, almost as if it were like a string. But to draw the antinode at the ends, and then the pattern here, we have the antinodes at the ends, and a node in the middle. This is the simplest pattern. It's just harder to draw the node and antinodes as what the longitudinal wave really looks like. So similar to the standing waves on the string, the wavelength is directly related to the length of this pipe. If we start at the left and trace the wave, we start at a peak, go down to the trough, I am seeing 1/2 of a wavelength on within the length of this pipe. So this simplest pattern, we're seeing a wavelength of 2L. This is called the fundamental pattern. It looks different from the fundamental pattern with the string, but this wavelength is 2L, just like the string was. The frequency that would cause this standing wave to form is called the fundamental frequency. We use an F1 to represent it. It's going to be the speed over this lambda 1, so the speed over this wavelength. This speed, though, is the speed of sound in the air that is within the pipe, because we're talking about a sound wave passing through the pipe. So the equation itself is very similar to what we were using with the string, but because we're talking sound waves, we have a different speed that we're working with. This would be called also the first harmonic, or first mode, meaning an M of 1. The next pattern, if we draw it similarly like the sine wave, we still have to meet this condition where we have antinodes at the end. We end up with an extra antinode in here. So antinode is where we're seeing the constructive interference. We're getting antinodes at the ends as well. Here we have 2 nodes. This is the next pattern. So this first pattern we drew was the fundamental. That's the simplest standing wave pattern in a pipe, an open pipe specifically. Here, if I trace the wave from left to right, I go down, back up to a peak. So I'm seeing a whole wavelength within the length of this pipe. So the frequency here will be the speed over the wavelength, but the wavelength is L. This is twice that fundamental frequency. This is considered then the second harmonic or second mode, meaning a mode number or harmonic number, M equals 2. We could continue drawing patterns. If I drew the next pattern within the pipe. Oh, I gotta try that again. Down, up, down. Whenever the end is open, we have to have the antinode there. Here we end up with another antinode. So within the length of this pipe, if I start at the left end and trace, there's a whole wavelength and another half. So 1.5 wavelengths on the length of within the length of this pipe. But again, 1.5 is 3/2. So we can say the wavelength is 2L over 3, which means the frequency is the speed over this wavelength. We're getting 3 times the fundamental, so this is the third harmonic, or the third mode, M equals 3. So if we wanted to write generic equations for an open pipe, they actually look just like the equations do for the standing wave on the string. We can say the wavelength of the mth mode, M is the mode number, or harmonic number. M is 1, 2, 3, 4, so forth. So there's multiple wavelengths to represent standing waves within this pipe. They're going to be different patterns, different number of antinodes in there, but all of these would be considered resonance of these standing waves. We can say the frequency of this mth harmonic is the speed over the wavelength, which ends up leaving us with mv over 2L, or m times the fundamental. Since we're talking sound, v here is the speed of sound in the gas that's within the pipe. So the wavelengths and the frequencies, these generic equations look the same as for the standing wave on a string, but we're dealing with sound waves, so the speed is different. And if we were to draw the pattern, that would look different as well. Now, the other situation we could have is a pipe that is open at one end, but closed at another, at the other, I should say. So open at one end, closed at the other. We already know the open end needs to be an antinode, but the closed end is a fixed end. So the closed end has to be a node. The open end has to be an antinode. So this is the simplest pattern drawn in terms of the sine wave. This is the simplest pattern we would see in a pipe that was open at one end and closed at the other. This is called the fundamental pattern. The frequency that causes this standing wave would be called the fundamental frequency. So coming back to relate this to the length of the pipe, like we have similarly before, if I start at the left end and trace the pipe, I'm going from a peak to zero. I'm going from a peak to zero. The whole wave would be peak to peak. In the open pipe, we went peak to drop. A peak to zero is only 1/4 of a wavelength within the length of this pipe. That means the wavelength here is 4L. So this is different than both the standing wave on the string as well as the standing wave in the open pipe. It is still true, though, that this fundamental frequency is going to be the speed over the wavelength. We still have the speed of sound in the pipe, in the gas within the pipe itself, and then the wavelength is 4L. So the wavelength is still directly related to the length of the pipe. We just have a different relationship this time because of one end being open, so we need an antinode, and the other end being closed, which means it will be a node. Something else interesting happens as well. If I draw the next pattern, so let me draw the pipe again. I have to have an antinode here. I would add an antinode in to get the next pattern. I tried. So we end up with a node. We have an antinode here, an antinode here, a node down here. So this new pattern within the length of this pipe, if I start at the left end, peak to trough, that is half a wavelength. And then getting up to the middle, this node is another quarter. So there's 3/4 of a wavelength within the length of this pipe. That means this wavelength is 4L over 3. If I put that into my frequency is speed over wavelength, I find that I have a 3 here, meaning this frequency is 3 times this fundamental we just looked at. This is considered the third harmonic or third mode, meaning our M number of 3. So we jump from a 1 to a 3. There's no 2, there's no M value of 2 that we would end up seeing. Our generic equations, we find if I were to draw the next pattern with another antinode in here, following the wavelength, I would have one whole wavelength and then another quarter. So that would be 5/4 wavelength within the length of the pipe, meaning the wavelength is 4L over 5. So this frequency, speed over the wavelength, we get a 5 in the numerator. So 5 times that fundamental. This is the 5th harmonic. It turns out with open-closed pipes, we only get these odd mode numbers. M can be 1, it can be 3, 5, 7, so forth. When you look at our equations in the test notes, it shows you that. So we can write our generic equations, the wavelength, let me do this, generic. These are specific for the open-closed pipe. It's open at one end and closed at the other. The wavelength of whichever mode number or harmonic number would be 4L over M. The frequency of the mth mode will be MV over 4L, or M times the fundamental, but M has to be odd. We do not get the even harmonics with an open-closed pipe. And so ultimately, having the different harmonics, what that means is if I had a tuning fork, so a tuning fork, the way they're made, they vibrate. So these ends vibrate back and forth. And they vibrate at very specific frequencies because of how they are constructed. If the frequency of this tuning fork matches any of the nth frequencies, it can be fundamental, it could be the 5th harmonic, the 7th harmonic. If those match any of them, we would hear this resonance set up, the standing wave. We would hear the sound louder than normal. Wind instruments, when you blow, they are still primarily playing the fundamental. And we will assume that still, unless a problem tells us to account for a different harmonic. But we do need to know whether we have an open pipe or an open-closed pipe, and we can then choose the appropriate equations for whichever situation we have. So in here, V is the speed of sound again, because it is a sound wave that is traveling through the pipe. So going back to what I mentioned, if you have a paper towel roll, just the empty, the towels are gone, you just have the inner tube. If you hit the side of it, you hear a certain pitch. And that certain pitch you hear is because of the length of the tube. By hitting the side of the paper towel tube, you're disturbing the air within that tube, and it's creating a standing wave. And since the wavelength is always related to the length of that tube or pipe, you will hear a specific frequency. It's not a clear, perfect, pretty sound. It's very dull, because that's not what it's made for. But you could still hear a very specific sound. So we'll do some examples and then move on to the next topic.